Good morning, everybody. My name is Gunther Leobacher. I am from the University of Graz in Austria, and it's a great honor for me to speak here at this CERN workshop. I would like to thank the organizers, Robert, Joel, and Stefan, for organizing the whole event, and I would also like to express my thanks to everybody who made this possible here. Today I will speak about two topics. I will give a brief introduction to Bose-Monte Carlo methods and their application. And in the second part, I will speak about numerical methods for stochastic differential equations, and in particular for those with discontinuous drift. This is the agenda for the first part, for Quasi-Monte Carlo. I will give a motivation why we need Quasi-Monte Carlo. I will explain what Quasi-Monte Carlo is, and then I will give some hints on how to apply Quasi-Monte Carlo. First, for the motivation, a central problem for many applications is to compute the expected value of a random variable x. And x could be, for example, a function of a price of a financial instrument in financial mathematics, or it could also be a function of some physical quantity, or more classically, it could be the payoff in a game of chance. It turns out that the most straightforward method for dealing with this problem is already one of the most efficient ones. For this, we generate a sequence of independent copies of our random variable, and then we estimate the expected value by taking the average of the first capital N copies of our random variable x. And this estimator has a number of favorable properties. For example, it's unbiased. This follows immediately from the linearity of the expected value. It's convergent by the strong law of large numbers. So this is one of the theorems in basic probability that we're using here. And if the variance of x is finite, we get a finite standard deviation for our estimator, and you observe that the estimator goes to zero. No, the standard deviation of the estimator goes to 0, like 1 on the square root of n. Now, what are strengths and weaknesses of this method? So a big pro is that it is a very simple and easy to implement method, in particular if you know how to generate those independent copies. And a bit of a backside is that more knowledge about the random variable x does not give better conversion speed. So whatever you do, you're always stuck with this conversion speed constant over square root of n. And the only thing that you can do is tweak the constant. This is the topic of variance reduction methods. Let me explain what I mean by more information about the random variable. So consider an example where we have a lot of information on the random variable, and it's very nice. So here we assume that x is the function of another random variable u. So f is assumed to be a C4 function on the unit interval, and u is assumed to be uniformly distributed on the unit interval. Then we can write the expected value of x as a one-dimensional integral, and we could do this, for example, by using Simpson's composite rule, and this gives an error estimate that is of the form constant times the supremum norm of the fourth derivative of f divided by the fourth power of n. So this is much faster than our Monte Carlo rate of 1 on square root of n. I want you to think about this. In all practical situations, x can be generated using a sequence of uniform independent random variables like this. So this means that x can be written as f of u1, u2, and so on, where f is a measurable function. And this here means has the same distribution. But still, in many situations, you can write x as g of u1 to ud, where u1 to ud are still independent uniform, but for a fixed number d. Which means that the expectation that we want to compute can be written as a finite dimensional integral over the d-dimensional unit cube. This means that now we are interested in computing integrals over the d-dimensional unit cube. We want integration algorithms for this, and d can be rather big, like in the hundreds or even thousands. And we don't want to use too many function evaluations. So the function evaluations are considered to be expensive. So this generation of the random variable capital X, or this evaluation of small g of u1 to ud, this is usually expensive. Since it worked so well in the one-dimensional case, we can now try to use Simpson's rule also in the d-dimensional case. That means the idea is to write our d-dimensional integral as an iterated integral d times. So this, of course, is Fubini's theorem here. And if we write that out, we get this expression here, so this iterated integral becomes an iterated sum, where we have this one-dimensional product rule. So these weights appear here. For example, this one-dimensional integration rule could be the compound Simpson's rule, like in the one-dimensional example. And you can work it out as an exercise that if g is 4 times differentiable, we still get the same error bound as in the one-dimensional case. We get c over the 4th power of n, but the small n now is not the number of function evaluations. Rather, the number of function evaluations is n to the power of d. So the error in terms of the function evaluations looks like this. We have c over the nth power of small n, but small n is the dth root of capital N. So what we get is the constant divided by n to the power 4 over d. And 4 over d becomes small if d becomes big. So if d is big enough, this becomes slower than our Monte Carlo speed of n to the power minus 1/2. And this is a phenomenon that shows for every one-dimensional rule with polynomial convergence order. That means if we want to have an error that is smaller than a given epsilon, we need more function evaluations than constant times 1 on epsilon to the power of d on 4. That is, the number of function evaluations needed to achieve a given error bound grows exponentially with the dimension. And this is called the curse of dimension. But remember that we already have an integration method which does not suffer from the curse, namely Monte Carlo. We can write our d-dimensional integral as an expected value, and we can approximate this using the Monte Carlo method. And we can even express the variance in these terms of integrals. So if we compute the variance, it looks like this, and this is again just a d-dimensional integral. So if this part here is finite, we get a convergence rate like from Monte Carlo, 1 squared or constant divided by square root of n. So the question that we are now asking is, can we do something similar but better? I'm now in a position to tell you what I mean by quasi-Monte Carlo. So if Monte Carlo is an approximation of a d-dimensional integral by this kind of averaging over a random sample, then quasi-Monte Carlo looks precisely the same, but now the function evaluations are not over some random vectors, but some cleverly chosen deterministic vectors in the unit cube. And this is a special case of the class of linear algorithms, where you have some weights. Those weights should sum to 1, but they are not required to be 1 on n. They can be also cleverly chosen if one has a good idea. You may recognize that our earlier attempt at using a d-dimensional version of Simpson's rule also falls in this category. So this can be good, so to say, or it could be bad for high dimensions. But in general, of course, linear algorithms cannot be worse than quasi-Monte Carlo since they are a special case. That is what I need to explain. If I tell you what quasi-Monte Carlo really is, I have to tell you what it means to have cleverly chosen integration nodes, and also you want to know what kind of error you can expect. I will only present one classic result in this context, the so-called Cox-Malavka inequality. This gives an error estimate for the error of integration of the following form. We have two factors. The one is the variation in the sense of Hardy and Krause of the function f. So this is a property of the function. And the other one is the star discrepancy of the points x1 to xn, which is a property of the point set. So I don't want to tell you exactly what the variation in the sense of Hardy and Krause is, but it is more regularity of the function f to have finite variation in the sense of Hardy and Krause than is needed for Monte Carlo. And in this context of the Cox-Malavka inequality, cleverly chosen point sets x1 to xn means that they have small star discrepancy. Now, although this classical result here is nowadays only one of many of its kind, this quantity d star here is still of a great theoretical and also practical interest. So I will take a couple of minutes to explain what this is. For the definition of the star discrepancy, we start with a set of n points in the d-dimensional unit cube, and we define the so-called discrepancy function. This is a function on the d-dimensional unit cube defined by this expression here. I have to explain what this interval here is. This is a d-dimensional interval defined like this. So this is just the Cartesian product of these coordinate intervals from 0 to yk. The first part of the formula measures the fraction of points in this that fall within this interval, and the second part is the Lebesgue measure of this interval. So here is the graph. We count the number of points that fall within this rectangle here, and we compare it by the Lebesgue measure. So if the interval 0y gets the fair fraction of points, the discrepancy function in y is 0. In other words, the discrepancy function evaluated at y measures the deviation from uniformity of the point set on this interval 0y. And now it's easy to define the star discrepancy of the point set x1 to xn. This is just the supremum over the discrepancy function, and so the right hand side depends on the point set x1 to xn via the discrepancy function, and of course a short way of writing this is as the supremum norm of the discrepancy function. If we recall the Cox-Malavka inequality, where the integration error is estimated by the product of the variation of f and the star discrepancy, then we can ask, what kind of convergence speed of the estimator can we expect if the variation is finite? So it all depends now on the speed with which the star discrepancy goes to 0, and there is a famous theorem by Roth from 1954 that this cannot happen any faster than this lower bound here. This leads to this formal or informal definition that a low discrepancy sequence is a sequence satisfying this upper bound. So we know it cannot go lower than this, but we say a sequence is a low discrepancy sequence if it satisfies such an upper bound, and constructions for such sequences exist by Halton, Foer, Sobol, Niederreiter, Xing, and others. But there is still a problem. While this bound goes to zero faster than n to the minus 1/2 asymptotically, it is increasing for small numbers, for small quantities of capital N. So this is the calculation. If we differentiate this, we see that this is greater or equal than 0 if n is less than e to the d. So this means that for practical values of capital N, if d is large, this method still is not of much use, or it's better to say this bound is not of much use. But also for this there exists some kind of remedy. So this is a concept that Sloan and Wozniakowski came up with in the year 1998. So the idea is that sometimes if you represent a random variable like this, then it might happen that not all of the input variables are equally important. So G might look something like this, that the variation in one coordinate is much more expressed than the variation in the other coordinate. And in such a situation, they got error estimates very similar to the Cox-Malavka inequality, where the error of integration can be bounded by a product where one factor only depends on the function g and the other factor only depends on the point sets. And this f here, this function space, is a space of coordinate weighted functions, which is usually a reproducing kernel Hilbert space. In recent years, a lot of research has been done on integration in weighted function spaces. However, actually the functions appearing in applications usually do not have the regularity required. But on the bright side, very frequently the faster convergence is nevertheless observed experimentally, at least if quasi-Monte Carlo is applied correctly. And so this is, on the one hand, it's bad news for applications because we do not have any strict error bound, but on the bright side, there is a lot of room for further research still. This concludes the first two parts of our first part of the talk. So I've given you some motivation why we want to use quasi-Monte Carlo at all. I have told you what quasi-Monte Carlo is, and now I want to talk about how to apply quasi-Monte Carlo. Recall that we want to use quasi-Monte Carlo to estimate the expectation of a random variable, and because of their similar form, QMC is often viewed as a drop-in replacement for Monte Carlo. So what do I mean by drop-in replacement? I think you just replace the random number generation by some low discrepancy sequence. But this is only true if x is of this particular form. So if we can represent x as a function of uniforms on the, of uniform independent random variables, then we can use this. And in particular, the dimension must be right. I have to use a low discrepancy sequence with the appropriate dimension. Then we may expect a significant gain in the convergence speed if either d is comparatively small or if the variables have very different impact on the value of g. So I refer to the theory of weighted function spaces. Let's have a look at an example. So this is just a simple function I came up with. We have the inner product of x with some vector a and apply the sine function. We have another inner product with another vector b and we square this. So I've chosen just some simple function that we actually can integrate, so it makes easy to compute the error. And this is a d-dimensional function, so the dimension is rather small. And here we see the corresponding error. We have on the x-axis, we have the logarithm of the function evaluations used, and on the y-axis, we have the log of the integration error. And what you see here is a rather typical behavior. We have a slope of roughly 1/2 if we use Monte Carlo, if we evaluate g at random points and take the average, and we get a slope of roughly 1 or almost 1 if we use a low discrepancy sequence. And this is rather typical. So this is the first try that I used to produce this graph. I was fairly certain that it would look like this from the outset. However, this is a simple example in that it is actually very low dimensional. It's only 4 dimensions. And to give you an example with higher dimensions, I will briefly talk about Brownian motion. And this will be one of the instances where we can make some coordinates more important than others. I will repeat the definition of Brownian motion. So this is a stochastic process B with the following properties. It starts at 0 almost surely. Then the increments are stationary, normally distributed, and the variance is the time difference. And moreover, if you have n increments, then those increments are also independent. And finally, we always require the path of the Brownian motion to be continuous. How can we simulate such a Brownian path? Now, the index set is the non-negative reals, and we have to make some selection on the times where we simulate the Brownian path. This means in practice we have to choose a discretization, so we choose small d times where the Brownian path will be generated, or for which there will be values of the Brownian path. So we construct a random vector, a Gaussian vector, so the Brownian motion at the d will be a normal vector with mean d and covariance matrix sigma. And sigma has this form. So here we have the first entry T1 in the first row and in the first column, and then we have T2 here, and then up to TD. So sigma ij is the minimum of Ti and Tj. With this, the entries have the proper correlation structure as the Brownian path, as we require from the Brownian path, and quite frequently we will take evenly spaced times, and here for this talk we will concentrate on this, some of which I will show you also works more generally, but most of it depends on this simplification. Now the question is, how do we generate such a Gaussian vector with this correlation matrix? So I have formulated this as an exercise. So if you have a D times D matrix which satisfies this equation, so A times A transpose is sigma, and you take a standard normal vector x, then A times x is a normal vector with mean 0 and covariance matrix sigma. So here is the calculation, but if I explained it to you, it would not be an exercise anymore, so I will skip this. So let us now look at two different constructions of a Brownian path. So the first is the so-called forward method, and in terms of the matrix decomposition of sigma, this is the matrix in question. So here we have D times D entries, and actually a 1 on square root of D is missing here. And here this is how our discrete version of the Brownian path is generated. So if you look at the matrix above and you multiply this with your standard normal vector, you see that this is just 1 on square root of D times x1, and then the second entry here sums x1 plus x2 and then divides this by 1 over the square root of D. And for B, we take the sum here over all the entrants and scale by 1 on square root of D. What this means is that our path is constructed from 0 to the end like this. So we make one step. So this is the 1 on D, times x1, and then we add the next increment, then the next one, and then the final one to get a discrete version of a Brownian path. In contrast, another important construction, the Brownian bridge construction, also known as Lévy-Ciesielski construction, proceeds in a different order. First, the endpoint is constructed using the first normal variable x1. So this already prescribes the general behavior of the path, so the average growth, if you will. Then you construct the deviation of the midpoint from the straight line, and then you proceed on the left half, the deviation here at 1/4, and then the deviation at 3/4. So this is a completely different kind of constructing this discrete Brownian path, and we also can give we can tell what the matrix is for this construction. So if A forward is the matrix corresponding to the forward method, then the matrix corresponding to the Brownian bridge is this matrix times the inverse Haar transform matrix, at least for if D is a power of 2. But a good question is, what difference does it make? I mean, from a probabilistic point of view, it doesn't make any difference, because those all are normal vectors with the same correlation structure. But it does make a difference if you use Quasi-Monte Carlo. For this, let us look at the impact of x1 on the behavior of the whole path for the different constructions. So what we're looking here is the role of x1. So in the forward method, we have a shift of the whole path, but only by a small amount. On the other hand, in the Brownian bridge construction, x1 determines the whole trend over the whole interval. So it looks like x1 has a much bigger impact on the whole shape of the path. On the other hand, if we look at the role that x7 plays, the seventh input variable, then we see that it's in the forward construction, it plays quite a similar role than as x1, in that we have a small shift of the path over a large period, but it's a very small shift. On the other hand, with the Brownian bridge construction, x7 only acts on this part of the path. So the overall shape of the path is dependent on x7 in a very little way. Whether or not the importance of the variable decreases with the index here also depends, not only depends on what we see here, so these graphs look convincing, but actually it depends on the function where we plug the Brownian path into. So if we have a function that very much depends on the overall behavior, so on the average growth, then the Brownian bridge construction will have this property that the first variable is much more important than later ones. And one example where this happens, but I will not write it down, is the Asian option in finance. And here we have different constructions. So here the forward construction gives this error. So here again is the number of points. Here is the error, both logarithmic. And the Brownian bridge constructions, here two variants of this, give a much better convergence. And here we have a third construction, the PCA method, where the matrix A is the singular value decomposition of the matrix sigma. And here I've written it down. So the thing why this works so well here is because an Asian option is an option that depends on the global trend of the Brownian path mostly. I would like to conclude this part with some cautionary remarks. The preceding results about the Asian option are only experimental. They seem to work quite well in practice, but we have no sound proof about why they work. And the problem is, although the random variable has the proper form, so there's a function such that we have d uniform input variables, and even we can put more weight to the first input variable using the Brownian bridge construction or PCA. The problem is that G does not belong to any of the known classes for which error bounds exist. And the problem is that G is unbounded and non-smooth. So why this works remains a bit of a mystery, and the good news is that this is an opportunity for further research. So this concludes part 1, the introduction to Quasi-Monte Carlo methods and hints about their application. And we will soon start with the next part of the talk. I'll give you an outline about the second part of the talk, which is about stochastic differential equations. I will start with a motivation why one is interested in stochastic differential equations, and particularly from the point of view of mathematical finance. Then I will recall some classical results about stochastic differential equations, like existence and uniqueness results, and also numerical schemes. And finally, I will talk about a bit of my own research, stochastic differential equations with discontinuous drift. What is the motivation for considering stochastic differential equations?
Well, first of all, if you think of ordinary differential equations, then you know that they serve as mathematical models for many phenomena in all kinds of disciplines, most prominently in physics, biology, economy. For example, there is the simple growth of bacteria in a petri dish where you get a good model by stating that the change in the population is proportional to the size of the population with a factor A, which is the growth factor, and it's also well known that this leads to exponential growth. Another model is logistic growth, so this would be the same phenomenon, but here you model it with limited resources so that the rate of the growth decreases with the population size. So here we don't get exponential growth, but we reached some equilibrium after a long time. Other famous models are the predator-prey model, or also very prominent in recent months, the SIR model for modeling epidemics such as the current corona pandemic. Also very well known is compound interest in continuous time, where the capital at time t grows exponentially with growth rate delta here, and delta is this number here where r is the interest rate. So this is very similar to the bacteria growth, and so it solves the same, or it's not similar, it's the same as the bacteria growth, and it is modeled by the same differential equation. And of course you get more interesting models if the interest rate can also depend on the capital and on the time. And in all of these models, we have stochastic influence in the real world counterpart. So strictly speaking, the bacteria doesn't really grow like exponentially, but there's a small perturbation because of environmental factors, and the same is true for all the other phenomena, although in many of these applications the fluctuations are negligible. But on the other hand, quite often they are not, and we do have some stochastic influences. For example, if you invest your money not in some fixed interest investment, but in a share, then, well, you expect it to grow. And, well, for example, the price of most company shares grows over time. But obviously, as you know, the stochastic influence on this growth is surely not negligible, and, well, the share prices go up and down, and it looks very random. Here, for example, we have a current picture of the share of the Apple company. So, well, this already looks pretty much like exponential growth, but there is some fluctuation. So this is exponential growth with noise. And this is not really a special case. For example, if you look at Microsoft, it looks pretty similar. Maybe the fluctuations are here a bit smaller. What we also observe is that we get a small distortion when the share value is small, and we get large distortions if the share value is large. So, well, from the picture we cannot say that it's really proportional, but on the other hand, it doesn't look as if it was not. So it is not completely out of hand to model it like this. So we have growth like the exponential growth, but the growth rate is perturbed by some noise. And the noise is also amplified by the current value. and what we still have to explain what we mean by white noise. Of course, informally we would think of white noise, we have many small impulses that change the share price over time, and they add up to those larger fluctuations that you see in the curve. Of course, if you look at another stock price, for example, Volkswagen, then here you can say maybe this is exponential growth here, but then again we have some steep drops here and here, and we can also give a reason for this. So the first drop is the emission scandal, and the second drop is the current COVID pandemic. The latter is also visible in, or is also present in Apple and Microsoft, but it's less expressed because the overall trend is stronger growth. Why I show you that share is because, well, those big drops are not covered by the model I showed you earlier. So we have to, there are other models like jump diffusions that can also deal with this, but I'm not going into that. So we stick with this model here, with our growth model proportional to the price, and with this white noise here. And the question seems to be, what is white noise? And it turns out that it's not the best idea to really give a mathematical model for that, but rather we think of white noise as a process that if we integrate it, we get Brownian motion. And the thing is, this Xi, if you try to write something down like this, you do not really get the function. And on the other hand, it turns out it's not really necessary to get the function, because we can start with this. So still, it's not a problem to write the Brownian motion as a sum of independent random variables by writing it as a telescopic sum of its increments. And then if I rename and rescale this, then we get an expression like this, which looks a bit like a Riemann sum. But again, if you let n go to infinity, you do not end up with a real function here. That is, the better question is, how do we get a sound mathematical interpretation of this equation if we accept that this here is cannot be really modeled as a function, but still can be thought a bit like this. And the solution to this is provided by the Ito stochastic calculus. And in the next couple of slides, I want to give you a flavor about how this works. First, let us look again at ordinary calculus. So if we have some continuous functions f and g, then we can evoke the fundamental theorem, which says that if the derivative of x is f, then we can write x of t as x of 0 plus the integral over f. And if we postulate some stochastic version, that of course we need first to develop, but if you postulate a stochastic version of this, this would look like this. The derivative is f of t plus some function g of t times white noise. So in our earlier example, this was b times x of t. But this is more general now. So by this would be equivalent to the integrated version here. And if the integral is linear, we can split this in two parts. And here we have a part that is uncontroversial, but here
we have the integral over g times xi, and xi is still not a function, but is what we think of white noise. So what do we do with this part here? Maybe it helps to look at some other type of integral. So recall the so-called Stieltjes integral. If alpha is a differentiable function, then the Stieltjes integral over g with respect to d alpha is defined as the integral over g times alpha prime. So we think we would, if we could use this for the stochastic integral, then we could think that the stochastic integral is this here. But the problem is, this is still not a function, and the problem is that the paths of B are almost surely nowhere differentiable. So this is why Stieltjes integral does not work in this way. Okay, now you may say that for Stieltjes integration you don't need differentiability of the integrator, but only bounded variation. Well, this is true. The path of B would not need to be differentiable but of bounded variation, but this is also not the case. Almost surely is every path of B not of bounded variation. Thus, the first task of Ito calculus is to make sense of this kind of integral with respect to Brownian motion, and this will be called the Ito integral, and, well, of course, we need a suitable class of functions for which this is defined. And if we have this, then we can go back to our exponential growth with a random perturbation. So we would write the differential equation like this formally, and in integrated form like this. So here we have the ordinary integral without the disturbance, and here we have our stochastic integral. A bit more generally, now we want to really define what we mean by a stochastic differential equation. So we are given two functions mu and sigma from the positive reals times the reals into the reals, and those are supposed to be measurable functions, and we want to study equations of this form. Xt is x0 plus ordinary integral over mu sxs plus Ito integral over sigma sxs dbs. So the equation of this form is called a stochastic differential equation with coefficients mu sigma. And of course we are interested in existence and uniqueness of solutions, and under this weak conditions on mu and sigma, there is obviously no guarantee that there will exist a solution. This concludes the first part of the second part of my talk, and tomorrow I will start with the second part of the second part, the classical results about stochastic differential equation. So thank you very much for listening or watching, and see you tomorrow.